Our third perfect problem for Math 251. The idea here is you're given a function, this third degree polynomial, and asked to find its derivative. But you're not using any of the clever chapter 3 tricks. You're doing it the long way, the hard way. You're doing it by using the difference quotient. So you're first finding f prime of a using the difference quotient. So what you need to know is that f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all divided by h. So I need to evaluate this limit right here to find f prime of a, and then I can change the letters to get f prime of x. So that's part one here. Well, what I can do is I know f of x is x cubed minus 2x plus 1, so I can kind of go through and plug that in. I can say that this is the limit as h approaches 0 of, and then instead of f of a plus h, I can copy this thing here, except everywhere I see an x, change it into an a plus h. So I'd get a plus h cubed minus 2 times a plus h plus 1. And this thing is f of a plus h. From that I want to subtract f of a, which is this, except everywhere you see an x, change it into an a. So subtract a cubed minus 2a plus 1. And then this entire thing, don't forget, is all divided by h. So my goal is to evaluate this limit, and to do so I want to simplify this fraction here. Rational expression, I guess, if you're being really technical. So the way I'm going to do that is get rid of all the parentheses. So to get rid of these parentheses, I have to cube a plus h. And that's not as easy as just cubing the a and the h. Think about it like FOIL, but twice. So a plus h times a plus h gives you a squared plus 2ah plus h squared. And then if you multiply that times a plus h, what you'll come up with is a cubed plus 3a squared h plus 3ah squared plus h cubed. So this expands to this. And then you want to subtract 2ah. So I got minus 2a minus 2h. Essentially, I'm taking this negative 2 and distributing it through the parentheses. And then plus 1. And then over here, I'm going to distribute the negative through the parentheses to get negative a cubed plus 2a minus 1. And that entire mess gets divided by h. And that's about as bad as things get. Actually, things turn out pretty nicely here. What you now do is stare at this thing and try to simplify it. Well, hey, look, I got an a cubed here and an a minus a cubed here. Nice, those go away. What about I have this minus 2a and this plus 2a. Nice, and I have this plus 1 and this minus 1. Cool. A lot of stuff cancels out. What you're left with when the dust settles is 3a squared h plus 3ah squared plus h cubed. So this I already canceled out. I wrote down those three. The minus 2a I can cancel out. And then I have this minus 2h right here. And then I have this plus 1, but this minus 1 cancels it out. This a cubed I already canceled with this a cubed. And this plus 2a I already canceled with this minus 2a. So I get that divided by h. And what you notice here is that each term in the numerator has an h in it. So I can factor out an h from each term in the numerator and cancel it with this h in the denominator. To get that this is the limit as h approaches 0 of 3a squared plus 3ah plus h squared minus 2. So that one of these h's, one of these, one of these, and one of these canceled with this guy. And the nice thing about canceling this h is now it's easy to evaluate the limit. Now I can change all the h's into zeros without worrying about dividing by 0. So if you change all your h's into zeros, this term goes away and this term goes away, and what you're left with is 3a squared minus 2. But that's f prime of a, and really we were supposed to figure out f prime of x. So I guess I could say, okay, so f prime of x must be equal to 3x squared minus 2. And as you'll see, as you might already know, there's a lot easier way to get from here down to here. But it relies on stuff we haven't yet learned. And right now, all we can do is evaluate these limits, and that's how you do it. So that right there is f prime of a, and I guess that answers part 1. Part 2 says, okay, this f prime of x thing, because you're using x as the variable, you might be thinking about it as a function. If it's a function, you can graph it, so graph that thing. All right, guess I can do that. So here's a graph. 3x squared minus 2. Well, what that means is the vertex of my parabola shifts down by 2. And then I want to, well, really what I want to do is stretch it vertically by a factor of 3. Stretch x squared vertically by a factor of 3. And then subtract 2, so shift it down by 2. Maybe easier just to plug in points. So if I plug in 0, negative 2 comes out. If I plug in 1, then positive 1 comes out. And if I plug in 2, 2 squared is 4, times 3 is 12, minus 2, 10 comes out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's some nice symmetry going on with this parabola, that when I plug in -1, +1 comes out, and when I plug in -2, +10 comes out. And so what I end up with is a graph that looks something like this. It's hard to sketch graphs on a computer. That's actually pretty darn good, to throw myself a compliment. So this right here is f prime of x. There's your derivative graph there. Sketch a graph of f prime of x. Done. What about 3? Use your graph of f prime of x to determine where f is doing these things. Okay, so f is, so this is part 3, increasing when f prime of x is positive. It's greater than 0. So where is this thing greater than 0? Well, I guess I should figure out those values. From this point all the way out here. Okay, I guess I need to figure out those points. So I really want to know where the intercepts are here, where the x-intercepts for my function is. So what I can do is I can say, all right, 3x squared minus 2 equals 0. So 3x squared equals 2. So x squared equals 2/3. So x is equal to plus or minus the square root of 2/3. So what that means is that this point right here is at the square root of 2/3. And this point right here is the negative of the square root of 2/3. And now that I have those points labeled, it's easier for me to point out when my function is increasing, because my function is increasing when my derivative is positive, and my derivative is positive as long as I'm less than this point or greater than this point. So that happens from -infinity all the way up to the negative of the square root of 2/3. And then it happens again from the square root of 2/3 all the way up to positive infinity. And similarly, f is decreasing when f prime of x is less than 0. And it's less than 0 kind of in between those points. So from negative square root of 2/3 all the way up to the square root of 2/3. So I guess this is part A here. Part B says, okay, what about when is it concave up and concave down? F is concave up when f prime, it's weird that I'm using the x here and not here, so fine, f of x is increasing, f of x is concave up when f prime of x is increasing. So when is f prime of x increasing? Well, it looks like everywhere from 0 to infinity on this kind of right-hand side of the parabola. So it happens from 0 to infinity. And similarly, f of x is concave down when f prime of x is decreasing. So that's going to happen everywhere from -infinity to 0. When does f have a local maximum or a local minimum? Local, well, that didn't work out well. Local max happens on f of x when f prime of x, if you picture a local max, you're thinking like a, I don't know, a hilltop. So what's going on is your function used to be increasing to get up to that hilltop, and then it's decreasing to go down the hilltop. So increasing and decreasing we can describe in terms of the derivative. So the function's increasing, as we saw up here, when the derivative is positive, and it's decreasing when the derivative is negative. So local maxes happen when f prime of x changes from positive to negative. It used to be going up, now it's coming down. There must have been a local max right there. Similarly, a local min happens on f of x when f prime of x changes from negative to positive. So where does that happen? Well, let's look at f prime of x here. I have it graphed. It looks like it changes from positive to negative right here at the negative square root of 2/3. So it changes from positive to negative at the negative of the square root of 2/3. and it changes from negative to positive right here. The derivative used to be negative, now it's positive. At this point it switched. That point is the square root of 2/3. So it has a local max there and a local min there. I think there's one more problem, right? Inflection points, all right. So f has an inflection point. When the second derivative changes sign. So where does that happen? Well, if the second derivative is changing sign, that's saying that the first derivative changes from increasing, changes maybe increasing, decreasing. Cut down on words here. And so the logic there is the second derivative is the derivative of the derivative. So you think about this in terms of a function. If the function changes from increasing to decreasing, then its derivative is changing sign. Anyways, f has an inflection point when this thing happens. So when does the first derivative change from increasing to decreasing? Looks like that's right here. Right? Looks like that happens at 0. So that happens at x equals 0. Fine, good enough. So now I have all this information about this graph in 3. In 4 it says, okay, so then sketch your graph. Well, I went ahead and let Google do that for me. If you type in x cubed minus 2x plus 1, you get a graph that looks like this. So note that I have this local maximum here and this local minimum here. My maximum is at this point that looks like it's a little bit less, a little bit more than -1. And then I have this minimum at some point a little bit less than +1. And those points correspond with the negative square root of 2/3 and the positive square root of 2/3. So I think that's enough information for me to draw my graph. Maybe I should make sure I get my y-intercept right. It looks like the y-intercept is at 1 here. And then we just barely dip below the x-axis. And yeah, I think I can draw this thing. So I got something that kind of looks like this and then goes up that way. And then we sort of have it going like this. And then this point right here is at the negative square root of 2/3. And this point right here is at the square root of 2/3. And you can go and confirm all this stuff. My function is supposed to be increasing from -infinity to the negative square root of 2/3. Yep, looks like it's increasing right there. Oh, and then again from 2/3 to infinity. Yep, it's increasing over here. And it's supposed to be decreasing between those two values. Yep, that's exactly what's happening. It's concave up from 0 to infinity. So we kind of have this bowl shape here, a right side up bowl, I guess. Whereas it's concave down from -infinity to 0. So check out this shape. Looks like an upside down bowl. It's concave down. Local max happens at the negative square root of 2/3. Yep, local max. Local min, maybe I'll label all these guys. Local max, local min. We have an inflection point where it switches from concave down to concave up is right here. And then I'll say in this direction, it is concave down. Whereas in this direction, it is concave up. And I'm kind of short on room. I'd like to show increasing and decreasing. So maybe I'll do that somewhere. I don't know, here I guess. Sure. Over here, it's increasing. And over here, it's increasing. Whereas between these two, it's decreasing. And maybe now I put so much information in there that you can't read any of it, but at least I talked through it all. So I'm going to go ahead and call that good and end this video here.